Hey, in this video, we're going to be talking about earthquakes, a little bit about the general nature of them, what causes them, and how we measure them. So first of all, what causes them? All right, earthquakes are caused by the rapid release of elastic energy in rocks that end up causing a vibration that we can feel here on Earth. All right, the theory that surrounds earthquakes is called elastic rebound theory. All right, and that is that the rocks want to move. All right, just like if I took a pencil, all right, and I apply a stress to it, all right, what's going to happen at first is it's going to bend a little bit, but it can't keep on bending forever. All right, eventually it's going to get to a point where that energy that's built up there wants to be released. All right, and when that energy is released, there's a lot of motion that is caused, and that's what an earthquake is. All right, earthquakes tend to occur at faults and plate boundaries. All right, so this slide right here gives a good visual description of what happens in elastic rebound theory. All right, you can see a bit of crust right here. All right, so that's like one, so this right here you can think of one solid block. All right, and you can see that there's a fault right there. That's a break, that's where two separate rock surfaces are touching each other. All right, so this uh, this piece of land right here on this plate is wanting to move in this direction. All right, the land on this side of the fault is wanting to move in the opposite direction. All right, so this would be a transform fault. All right, it's that transform boundary where they're going side by side. All right, you don't have one plate wanting to go underneath the other. They're not both moving towards each other. They're kind of moving sideways relative to each other. All right. And what ends up happening is this this side right here, it's wanting to move forward, and there's a certain at first it doesn't move. All right. The rocks kind of get caught on each other. All right. And but they still eventually it wants to move. And so what happens is the rocks get caught and a lot of energy builds up, it builds up, it builds up, and then all of a sudden it slips really fast. All right. And there's a lot of energy that's given off. All right. So it's at that moment where the rocks slip that's when the earthquake is occurring. All right. And um, the I guess if there's any benefit to an earthquake, after the earthquake, that stress is relieved. All right. So in a lot of ways, it's actually better to have a lot of small earthquakes than it is to have one large one. Because if you have lots of small earthquakes, you're constantly, if my hands are moving next to each other, as long as the energy is constantly being released, nothing big happens. But if a lot of energy builds up and then it's all released at once, then it's a really big earthquake. So as we said, most of the energy or most of the earthquakes in the world occur along the plate boundaries. All right. So if you were to locate, every yellow dot on this map represents an earthquake location. All right, and you can see that most of them lie along the plate boundaries. And the most famous plate boundaries are the ones that surround the Pacific Ocean. All right. What we call the Ring of Fire. All right. So even though it's called the Ring of Fire because that's where so many volcanoes are located, it's also where so many of the earthquakes are occurring. So there's two very important terms that have to do with an earthquake. All right. So what this diagram right here shows is you've got a fault. All right. And again, this is going to be one mass of rock right here. This is going to be a different mass of rock. All right. And let's say that this rock right here on this side of the boundary wants to move in the direction of the arrow. All right. And again, the rocks are going to get below the surface. They don't tend to move smoothly. They tend to get caught up on each other. The little snags that are part of just the natural shape of the rocks prevent them from moving smoothly like I can move my hands across each other. But the area at which point where the snag finally releases, that's what's called the focus. All right, so that's where the earthquake actually happens. All right. The thing is, no one feels it at the focus because no one lives at the focus. All right. People don't live underground. They live on the surface of the earth. All right. So the people that would feel the biggest effect from the earthquake are the people that are directly at that spot on Earth above the focus. All right. And the name for that place is the epicenter. All right. So a lot of times people think of the epicenter as that's where the earthquake occurred. Remember, where the earthquake occurred is directly below the epicenter. All right. So a lot of times when earthquakes, or generally when earthquakes occur, you don't just have one shaking. All right. You generally will have movements, small little earthquakes that happen before and after the major earthquake. All right. And if something happens before a major earthquake, if something happens after the earthquake, we call that an aftershock. And the small earthquakes that happen before are called foreshocks. All right, and these can happen even days before a major one. And if you live in regions of the world where they have a lot of earthquakes, when you feel a small earthquake, a lot of times you have to be very concerned because that might be the sign that a larger one is going to be coming. Okay, so even though the earthquake is caused when the rocks slip, all right, that energy is transmitted through the earth with what are called seismic waves. All right, and there are three major types of seismic waves. There are primary waves, secondary waves, and surface waves. All right, so the first of these types of waves is primary waves. All right, and a primary wave is what's considered a compression wave. All right. And it's the one that it travels through the Earth's interior. It's the fastest moving of all the different types of waves. All right, so we talked about there's primary, secondary, and surface. The primary one is the fastest. All right, and one thing about primary waves is it passes through any type of material. All right, both solids and liquids. All right, one way to remember the term is when you think of primary wave, think push, pull. All right. So think push and pull begin with that. And so if you think about this little block right here, think of it like a slinky that if you hold one end of it and you give it a quick push with your hand, it's going to cause a little bit of a wave to go through that slinky. All right. All right. Again, so think push, pull wave. So the next type of wave, just like a primary wave, travels through the Earth's interior. All right. This one's called a secondary wave. And the reason that it's called a secondary wave is that it travels slower. It travels slower than the primary waves. All right. One thing, a little bit of analogy that you can use is lightning and thunder. All right. So we know that light travels faster than sound. All right. And because of that, we see lightning before we hear the thunder. All right. So the faster thing gets to us first. So if we were to say there is a primary indication that a lightning strike has occurred, and that's the flash, all right, the lightning, the thing that we can see with our eyes, all right. It's the primary thing because it gets to us faster, all right, so it gets to us first, all right. The secondary evidence that a lightning strike has occurred is the thunder, all right. So that's the thing that gets to us second, and the reason that it gets us to us second is because it's traveling slower than the lightning, all right, than the light from the lightning. Okay, so they travel through the Earth's interior. They're slower. And one other thing that's different is that they pass through solids only. All right. So whereas primary waves can travel, let me go back to primary waves. All right. Primary waves can travel through both solids and liquids. All right. Um, the All right, so they pass through solids only. All right, and you can make the analogy with slinkies as well as with these types of waves, where instead of pushing on the end of a slinky, you give it a wave. All right, and I'm going to include a video that will show different types of ways that you can demonstrate these waves. Earlier in this unit, we talked about the layers of the Earth, all right? And one of the layers was the inner and outer core, all right? So a good question is, how do we know that these layers exist, all right? Well, we've learned about these from studying S waves and P waves, all right? So let's say that an earthquake happens on this side of the Earth, all right? We'll use this example right here. On this side of the Earth. Could could you sense that earthquake over here? All right. Well, with a P wave, well, that wave would have, so since it goes through the earth, if you make a kind of a line, all right, we can see that, oops, go back here. Since P waves can go through both solids and liquids, all right, this wave right here would eventually make it to this part of the earth over here. So you could detect that P wave on this side of the earth from an earthquake that happened on this side of the earth. And that's because it can go through all types of materials. All right. But if with that very same earthquake, you can't detect the S waves at this position right over here, because that would require that wave to go through a liquid material, and S waves can't go through a liquid material. So we've actually benefited from earthquakes in that we've been able to figure out a lot of what's on the inside of the earth by studying these different types of waves. And the last type of wave is a surface wave, all right? And a surface wave, as the name would indicate, is something that travels just along the surface of the earth, all right? So, and the thing about the surface waves is that they're the slowest wave, but they're also the most destructive. When you think about all the damage that gets created in an earthquake, most of those are done by the surface waves, all right? They move very much like an ocean wave. And what I mean by that is, if you've ever been in the ocean and you've got a big wave coming towards you, what's one way that you can protect yourself? Well, if you're deep enough, you can just go underwater. All right. And if you go underwater, that big wave just goes right over top of you. And you might feel a little bit of it, but if you go deep enough, you don't feel it at all. All right. So if you think about, look at this little diagram right here. If you were the material at the very bottom moves very little, all right, but the material at the top moves a lot, all right. So the deeper, once you get to a certain depth underground, you don't experience surface waves because they're only at the surface.